Okay, so we're going to continue with the Taylor series chapter. So previously we looked at finding what the Taylor series was, so finding the coefficients for that summation. Now we're going to look at finding where it converges. So in those examples we looked at last time, we saw that some of them converged everywhere. There was no problem with convergence. And other examples had a problem outside a certain interval. So we want to see where, in fact, does this converge. Okay, so let's say we have our function f of x is equal to the sum from n equals 0 to infinity cn x minus a to the n. So that's some general Taylor series. Given this function f, we can calculate these coefficients and we get our series. Now the question is, for which values of x does this right-hand side converge? So for which values of x does this right-hand side converge? Okay, so on the left-hand side we have f of x. We can just substitute a value of x and we get the result. But this right-hand side is an infinite series. And we know from the last chapter that sometimes a series will converge, other times the series will diverge, depending on what we have inside. So given a particular value of x here, does this right-hand side converge? And if it does it converge to the right value? Okay, so these are the questions we're going to answer in today's lecture. Okay, so just a little bit of notation. The interval of convergence is given by a minus r to a plus r, where this capital R is called the radius of convergence. Okay, so if we have our number line here, x, here's a. Remember, when we take the Taylor series, we can shift it to some value a. Then we get this interval from a minus r to a plus r. On that interval, our series will converge. Now, there's different options. We can either have the interval being 0. In other words, it only converges at the point a. So that's the first possibility. Or there's some finite r. So we have, for example, -161, where it converges. And the third possibility is if r is infinity, we can have any x value. Okay, so those are the three possibilities that we can have. So given a particular Taylor series, we want to see which of those possibilities it is and what is this interval. Okay, so let's have a look at some examples to show this. Okay, so example number 1 is if we have the sum from n equals 0 to infinity x to the n. Okay, very simple. Remember, this is for the geometric series. Okay, where the ratio is x. So we have 1 plus x squared plus x cubed and so on. We've got that common ratio of x. And we would like to test for which values of x does this converge. Now we know the values. We should have the common ratio having absolute value less than 1. But let's try and show that using what we know about series. So to test if this converges, we can use the ratio test. Okay, so we looked at all of these tests previously. So with the ratio test, what we want to calculate is the limit as n goes to infinity. The next term, so n plus 1, over the current term, which is x to the n, we calculate this ratio. Okay. Then once we take the limit, we get a value, and then from the value, we can see if it converges or not. So remember, on the side here, if it's less than 1, then it converges. If it's greater than 1, then it diverges. And if it's equal to 1, it's inconclusive. Okay, those were the three criteria we had with the ratio test. Okay, so let's calculate this. So we have the limit as n goes to infinity, x to the n plus 1, we can write as x to the n times x over x to the n. Now we have an x to the n at the top and at the bottom, we can cancel those. Now there's no more n, so the limit doesn't do anything here, so we just have the absolute value of x. Okay, so that's what we get. Now for this to converge, let's look here. If it's less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, it's inconclusive. We want to find the values of x where it converges. So we're going to take this limit value, absolute value of x, and we're going to say what happens when it's less than 1, because that means it converges. So from here, we can rewrite this as minus 1, less than x, less than 1, okay, just using the definition of the absolute value. And we see that on this interval, it will converge. Outside this interval, it will diverge. Okay, so this minus 1 to 1 is the interval of convergence. Okay, outside, it doesn't work, okay? It goes up to infinity. But between these two values, we get a finite answer. Okay, so that's the first example. Let's have a look at something a bit more difficult. Okay, so here we have the sum, n equals 0 to infinity, n factorial x to the n. Okay, so let's say this is one of the Taylor series that we get. We want to know for which values of x does this converge. Okay, or in other words, what is that interval of convergence? So again, we use the ratio test like we had before. So we calculate the limit as n goes to infinity, absolute value. We want to look at the next term divided by the current term. So the one with n plus 1 divided by the nth term. So that will be n factorial x to the n. Okay, so we calculate this. Once that's done, then we can see where it converges, where it diverges. Okay, so here we can clean this up a bit. So we have the limits as n goes to infinity, n plus 1 factorial, we can write as n plus 1 times n factorial. So n plus 1 times n factorial. That's just using the properties of the factorial. So remember, something like 3 factorial is 3 times 2 times 1, or 2 factorial is 2 times 1. So 3 factorial we can write as 3 times 2 factorial. Okay, because it's 3 times 2 times 1. Or if we had 5 factorial, that's 5 times 4 times 3 times 2 times 1. Or we can write that as 5 times 4 factorial. So 5 factorial, that's 5 times 4 times 3 times 2 times 1. But 4 times 3 times 2 times 1, that's 4 factorial. So it's just 5 times 4 factorial. Okay. So n plus 1 factorial will be n plus 1 times the factorial of the previous bit. Okay. Sorry? Yeah, so we minus 1. So here, this is n plus 1. So it will be n plus 1 minus 1, so it's n. Okay. If we had n factorial, then it would be n times n minus 1 factorial. Yeah, we're always going down. Okay. Then x to the n plus 1, we can write as x to the n times x, divided by n factorial x to the n. Okay, so why did I separate this factorial? Because if I have n plus 1 factorial at the top and n factorial at the bottom, n plus 1 times n factorial, but the bottom is also an n factorial, so they cancel. So that and that, they go away. Okay, so no more factorials once we cancel that. Then at the top we have x to the n, and the bottom we have x to the n, that can also go. Okay, that can cancel. So we're left with the limits as n goes to infinity, absolute value, x times n plus 1. Okay, now we can split the limits into two parts because this x, that has nothing to do with n, we can take that out. So this will be absolute value of x So we keep the absolute value, but it just comes out of the limit. So this will be the limit as n goes to infinity, n plus 1. Okay, now we have a problem here. This limit here, as n goes to infinity of n plus 1, this is going to go to infinity. Okay, because it's the limit as n goes to infinity, so this n inside here will make it go off to infinity. But we want this to be less than 1, right, for it to converge. So the only way for this whole result to be finite and less than 1 is if this x is 0. That's the only way for this to be finite. So this whole limit bit here, this goes off to infinity. If we want the whole thing to be finite, it means this absolute value of x must be 0. Okay. Make sense? You confused? Okay. So this bit here, we have limit n going to infinity of n. So as n gets larger and larger, that limit is going to go off to infinity. It's going to get very, very big. But we want the whole result to be less than 1, like we had in this previous one here. Here. So when we did all the limits, we got to this step. But remember, if we're using the ratio test, the answer must be less than 1. So that's why we have this. So whatever our limit is, we want the limit value to be less than 1. Then it converges. But here, if we look over here, we see that that limit goes off. It gets bigger and bigger and bigger. So the only way for this to make sense and to be less than 1 is if x is 0.
So the whole thing's going to be...
Exactly, yeah. Yeah, so the whole thing will be 0, which we need for it to be finite. Okay, so we need x to be 0 for the whole thing, the whole limit and everything to be finite. So for the whole thing to be finite. Okay. So this means x is equal to 0. Okay, so if absolute value of x is 0, then x is 0, which means this Taylor series converges only at a single point. There's no interval, right? It has to be 0. So the series converges only at x equals 0. There's no interval. It's only at that single point. Okay, and that's because of this limit going off to infinity here. We have to have x being 0. Okay, that's the only possibility. Okay, so in this case, if it's only at a single point, we say that the radius of convergence is 0. Okay, it's like if you have a circle with radius 0, it's just the point. Okay, so here the radius of convergence is 0. Okay, because it's only at a single point. Okay, any questions on that? Okay, let's have a look at the next one. Number 3. Okay, so here we have the sum, n equals 0 to infinity, 1 over n, x minus 3 to the n. Okay, so we found the Taylor series, this is what we've got. Now we want to see what is the interval of convergence. Again, we use the ratio test. So for all of these, you use the ratio test. So we found the limit, n goes to infinity. We want the next term divided by the current one. So it will be 1 over n plus 1, x minus 3 to the n plus 1. Okay, so everything with the n, you put n plus 1, then divided by just the n, so x minus 3 to the n. Okay, so the top part, that's your a n plus 1, the bottom part, that's just your a n. Okay, so that's like the ratio test from before. Okay, so here we have the limits, n going to infinity, x minus 3 to the n plus 1, we can separate that out. So we have 1 over n plus 1, x minus 3 to the n times x minus 3, all over 1 over n, x minus 3 to the n. Okay. Now, in the top, we have x minus 3 to the n. In the bottom, we have x minus 3 to the n. We can cancel. Yeah. Now, in the bottom, we have divided by 1 over n. So that's similar to dividing by 1/2. If you divide by 1/2, that's the same thing as timesing by 2. Or if you divide by 1/4, that's the same thing as timesing by 4. So this 1 over n, we can take it to the top and just make it n. So we have the limits as n goes to infinity, n over n plus 1 times x minus 3. Okay, because the x minus 3 to the n, that got cancelled. Now this x minus 3, that has nothing to do with n, we can take it outside of the limit. Remember to include the absolute value. Limits n goes to infinity, n over n plus 1. Okay, now we want to calculate this. You can use L'Hopital's rule. That's fine. I'll show you a nicer method. So here we have x minus 3. Limits n goes to infinity. Let's divide the top and the bottom by n. So here we'll have n, and here we have n, 1 plus 1 over n. Okay, so I factored out an n from the top and the bottom. So here you could write times 1. So we took an n out of the top, and we took an n out of the bottom. Now they cancel. So we're left with absolute value x minus 3. Limit n goes to infinity, 1 over 1 plus 1 over n. Now, if n at the bottom gets very, very large, then 1 over n will get very, very small. So this 1 over n part over there, that goes to 0. So we have 1 over 1, which is just 1. So here we just get absolute value x minus 3. That whole limit just becomes 1, because that 1 over n becomes 0. So it's just 1 over 1. Okay, so we've got this as our limit value. Now, if we want this to converge, the limit value must be less than 1. So to converge, we must have absolute value of x minus 3 being less than 1. Okay, that's just straight from the ratio test. Now, if the absolute value of x minus 3 is less than 1, if we want to write that as an interval, we can use our absolute value properties, and we can write this as 2 less than x less than 4. Okay, so that's just using your definition for absolute value. Another way of writing this, we can say x is an element of 2 to 4. Okay. But that's just up to you. You can write it like with the inequalities, or you can write it like an interval. It means the same thing. Okay, so this is our interval of convergence. In other words, it's where our limit value from the ratio test is less than 1. So again, this is from the ratio test. Okay. Again, if you're unfamiliar with the ratio test or you need some more practice with that, look at the previous lecture on the series tests. Okay. And there's also some tutorial questions on these. Okay. Last example, number 4. Here we have the sum n equals 0 to infinity, minus 1 to the n, x to the 2n, over 2 to the 2n, n factorial squared. Okay, this looks quite complicated, but again, we just go through it step by step. So we're going to use the ratio test again. So we have the limit as n goes to infinity. We're going to look at the next term, so the n plus 1, divided by the nth term. So we'll have minus 1 to the n plus 1, x to the 2n plus 2. Okay, so remember here, if I put in n plus 1, it will be 2 times n plus 1. So it will be 2 times n plus 2 times 1. Okay, so make sure you don't put x to the 2n plus 1. Okay, so here we did 2 n plus 1, so it will be 2n plus 2. Okay, so just be careful when you substituting n plus 1, you don't just quickly write plus 1. Okay, make sure it's 2 and then brackets n plus 1. Okay, same thing with the denominator here. We've got 2 to the 2n, so if we substitute n plus 1, it will be 2n plus 2. Don't just write the plus 1 quickly. So it will be 2 to the 2n plus 2. And then here, we're going to have n plus 1 factorial, all of that squared. Okay, so wherever there was an n, I'll put the n plus 1. Now, we need to have this divided by another fraction, the nth term, but instead of dividing by the fraction, I can multiply by the reciprocal. So we can multiply by 2 to the 2n, n factorial squared, over minus 1 to the n, x to the 2n. Okay, so I divided by that fraction, but that's the same thing as multiplying by the reciprocal. Okay, so just make sure you swap the top and the bottom correctly. Okay, a few things can cancel right away. This minus 1 to the n plus 1 and the minus 1 to the n, they can go because we're taking the absolute value of this. So if it's positive or negative, doesn't matter, any negatives go away. So there and there, that goes away immediately. As for the rest of the terms, we need to expand out a bit. So this will be the limits as n goes to infinity, absolute value x to the 2n times x squared. Okay, just expanding that one out. Times 2 to the 2n times n factorial squared. I'm going to write that as n factorial times n factorial. Okay, just because I have two of them there. Okay, all divided by 2 to the 2n plus 2, that's 2 to the 2n, times 2 squared, I'm just going to write that as a 4. Okay, same thing here, we've got n plus 1 factorial squared, so I'm just going to write it twice because it's squared. So n plus 1 factorial, n plus 1 factorial. Okay, and then lastly we have the x to the 2n. Okay, now we can see what can we cancel. So we've got an x to the 2n at the top, x to the 2n at the bottom, they can go. We've got a 2 to the 2n at the top and a 2 to the 2n at the bottom, they can go. Okay, looks better now. Now we've got an n plus 1 factorial appearing twice. So we're going to use that same trick we had before. The n plus 1 factorial, we're going to write as n plus 1 times n factorial. So same as we did before. So this will be the limit as n goes to infinity. At the top, we're left with an x squared times n factorial times n factorial. In the bottom, we're left with the 4. N plus 1 factorial, I'm going to write as n plus 1 times n factorial for the first one, and then I'm going to do the same thing for the second one. N plus 1 n factorial. Okay, so why did I do that? Same reason as before. We've got these n factorials at the top, the n factorials at the bottom, they can cancel. So this first one can cancel this first one, the second one can cancel this second one. Okay, any questions on that step? Everyone good with that? Okay, now we've got n plus 1 and another n plus 1. I'm going to write that as n plus 1 squared. So this will be the limit, n goes to infinity, x squared over 4, n plus 1 squared. Okay, so it looks a lot better than what we started with. Now this x squared and the 4, that has nothing to do with n. We can take that out of the limit. So we have absolute value x squared over 4. We don't need the absolute value, but it's just good habit to keep it on. Limit n goes to infinity. Again, we don't need the absolute value here, but it's good habit. 1 over n plus 1 squared. Okay, so what is this limit going to be? It doesn't matter about the squared or the plus 1 or anything. We've got an n in the denominator. So in n, doesn't matter. Squared, plus 1, plus 2, doesn't matter. If n gets very, very large, 1 over n gets very, very small, which means the whole thing goes to 0. Okay, so n squared, n cubed, n to the 4, doesn't matter. If there's an n something in the bottom, it's going to go to 0, which means everything goes to 0. Right? Doesn't matter what the x is, since the limit is 0, it means everything is 0. Now we want to check, when does this converge? It converges when this limit value is less than 1. But 0 is always less than 1, so it always converges. So 0 less than 1, always. So it doesn't matter what x is. It can be any x value. The series converges for all x. Okay, so you can just say for all x, or you can say minus infinity less than x less than infinity. That works. X is an element of real numbers. That's fine. Or x is an element of minus infinity to infinity. Okay, just different ways of writing the same thing, but you use what's more comfortable for you. Okay, so we see that for this one, it converges for any x value. So here, whenever you calculate this limit and you get something less than 1, maybe it turns out to be a half. A half is always less than 1, so it always converges. Okay. If this number here was bigger than 1, then it will always diverge. Okay. Remember, if the limit value is less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, it's inconclusive. Okay. So depending on what that value is, we can say what happens to the limit. Yes?
Yes, I do not understand the factorial situation that happened at the yes, right here.
Okay, yeah. So we had this n factorial squared. So since it's squared, I just wrote it as times by itself. And then the same thing in the bottom, n plus 1 factorial squared, I just wrote it times by itself. Now this n plus 1 factorial, I wrote as n plus 1 factorial is equal to n plus 1 times n factorial. Like 5 factorial is 5 times 4 times 3 times 2 times 1. We can rewrite it as 5 times 4 factorial. So n plus 1 factorial is n plus 1 times and then the factorial of what's below it. Okay. And then I just did that twice for these two. Then the factorials cancel, and then I'm just left with the n plus 1.
That was that.
This bit on the side, yeah. Okay, yeah. That's just one of the properties that you need to know. But this does come up a lot whenever you have a factorial. So if you want to calculate these limits and you've got a factorial, you should be using this on the side here. Okay, it does help simplify things quite a bit. Okay, and then that just goes back to where we had here. Okay. Any other questions on this? Yep. Yeah, so if there's any factorial, so I'll do another example with that. So let's say we had this one, the sum n equals 0 to infinity, 1 over n factorial x to the n. Okay, so we've got another factorial there. So if we want to see where this converges, we can take the limits, n goes to infinity, 1 over n plus 1 factorial, x to the n plus 1. Okay, so that's the n plus 1 term, divided by the nth term, so 1 over n factorial, x to the n. Okay, we can clean this up a bit. So that will be the limits, n goes to infinity. The same thing as before, if you divide by half times by 2, so this n factorial can come to the top. And then we have the n plus 1 factorial at the bottom. At the top, we have x to the n times x, and the bottom, we have x to the n. Okay, so just put the fractions together. Now, x to the n and x to the n, they can go. So then we have the limits, n goes to infinity, n factorial times x, over n plus 1 factorial, like that. And now, again, we've got those two factorials. So we can use that property again. So this will be the limits, n to infinity. The top one we can leave alone, because the bottom one, that's the next one. So we're going to use the property on that. So it will be n factorial times x over n plus 1 times n factorial. Okay, so I'll write this on the side again. n plus 1 factorial is equal to n plus 1 times n factorial. Okay, so it's always times the previous. And again, these go away, and then we're left with the limits n goes to infinity, x over n plus 1. Now again, you can take the x out if you want, but we have the same thing as before. You've got the n in the bottom. If n goes to infinity, the thing goes to 0, so all of that goes to 0. 0 is always less than 1, so it always converges. Okay, so we've got another one where we can put any x value. And that's because this limit here, that went to 0. Okay. And then here we did the, let's highlight that. So that factorial thing at the top and this at the bottom. Okay, we managed to cancel that out. Okay, any other questions? Okay, I just want to show you on that Desmos the picture of the convergence. Okay, so let's just close this.